In 2026, the first uncrewed spacecraft will launch toward Mars. 2 years later, the first crewed flights are scheduled to depart. The ultimate goal is to build a self-sufficient city of 1 million people within the next 2 to 3 decades. The primary bottleneck for interplanetary colonization is escaping Earth's gravity. In the 1980s, putting a single kilogram of mass into space cost more than $75,000 using the Space Shuttle program. This data visualization shows the financial reality of that era. To build a sustainable Martian city, we need to ship about 1 million tons of equipment. Under legacy pricing, that logistics bill would exceed $1 trillion, making colonization economically impossible. That financial equation broke over the last 15 years. By building reusable, mass-produced rockets like Starship, launch costs have dropped to $200 per kilogram. We no longer face an absolute financial wall. Instead, becoming a multi-planetary species is now an active sequence of complex engineering problems that must be solved chronologically. Because Earth circles the Sun in 1 year and Mars in 2, they optimally align every 26 months, dictating strict launch schedules. To carry heavy payloads, rockets burn most propellant reaching low Earth orbit, where they dock with fuel-laden vessels before departing toward Mars. Getting there is a matter of patience. Arriving is a matter of surviving. The Martian atmosphere has barely 1% the density of Earth's. Hitting that thin layer of gas at speeds exceeding 20,000 kilometers per hour means you cannot rely on normal atmospheric drag to slow down. To bleed off that immense speed without crashing, the spacecraft will execute a maneuver called a belly flop. By descending sideways into the atmosphere, the ship uses its entire body surface to maximize aerodynamic drag, drastically reducing its velocity before rotating upright to use its engines for a controlled, vertical touchdown. Delivering hundreds of tons of cargo safely to the surface requires actively exploiting that dangerously thin layer of gas rather than fighting it. Once on the ground, colonists face a terrain of craters, dangerous slopes, and extreme cold. A viable landing site requires 3 specific features: a flat surface to land safely, a low elevation for slightly denser air, and immediate access to underground ice. This topographic map of Mars points us to the prime target. Scientists have identified Arcadia Planitia, sitting nearly 4 kilometers below the average surface at a latitude of 40 degrees. It offers safe landing planes, moderate temperatures, and shallow ice deposits. Breathing there requires manufacturing oxygen from an atmosphere composed mostly of carbon dioxide. NASA has already tested a device called MOXIE on the Perseverance rover. It captures Martian carbon dioxide, heats it to 800 degrees, and splits it into breathable oxygen and carbon monoxide, which becomes rocket fuel. To generate the hydrogen needed for that fuel, automated drilling systems like Redwater will melt and extract ice from beneath the Martian surface. This water will supply drinking stations, oxygen generators, and aeroponic greenhouses, where food is grown in suspended, nutrient-rich mists. The colonists also face solar radiation 50 times higher than on Earth, along with highly abrasive, toxic dust storms. Modular habitats will need to be coated with thick layers of water and the local dirt, known as regolith, to block cosmic rays and insulate the living quarters. Mars has just 38% of Earth's gravity, requiring intensive exercise regimes to prevent severe muscle and bone loss. And the mental toll of living millions of kilometers away will be managed by MarsLink. Using advanced laser technology, this satellite network will provide high-speed data transmission back to Earth, mitigating the isolation caused by massive communication delays. Every aspect of early survival rests on one engineering principle: in situ resource utilization. They must take the toxic atmosphere, the abrasive dirt, and the frozen ground and actively process them into the life support systems of a new civilization. The timeline for this outpost follows 4 phases. Autonomous robots will arrive first to level the ground and deploy solar arrays. Then, highly specialized human crews will assemble the first habitats. Over decades, modular construction will expand the base from a small outpost into a self-sufficient city of 1 million residents. Funding this expansion requires a multi-tiered interplanetary economy. Space agencies will underwrite the early scientific missions. Later, extracting strategic minerals like platinum and helium-3 from nearby asteroids will provide industrial revenue. Eventually, a commercial space tourism market will open, with ticket prices estimated at around €30,000 per passenger. The intense effort required to keep people alive in a completely hostile environment will drive rapid advancements in solar efficiency, atmospheric scrubbing, and water recycling. These closed-loop survival technologies can be applied directly to manage resource constraints and climate issues back on Earth. But the ultimate rationale for leaving Earth goes beyond economics or science. Building an independent, self-sustaining settlement on another planet serves as a permanent backup system for humanity. By distributing our species across multiple planets, we insulate ourselves against the very real possibility of a third world war, a massive pandemic, or a cataclysmic asteroid impact. Solving the engineering bottlenecks of Mars guarantees that whatever happens to our home planet, human civilization will survive.